Okay, today I'm talking about an actual technique used for natural language processing, and it has to do with sentence interpretation. And it's based on the original approach, which is the encoder decoder RNN model, where the encoder encodes an entire sequence and puts it in a vector, and the decoder will read from the entire vector and interpret the whole sequence. And that's a very basic approach. So the problem was that it didn't work super well as sequences got longer. So the improved technique is called self-attention, which is really good at determining the relative importance between words and how they're dependent on each other. So since that's a more dynamic approach, it's pretty good at working for longer sequences. So to start the technique, we have to convert the sequence of words into tokens and then the tokens to embeddings, where embeddings are really just a representation of each token, but using a bunch of numbers. So there's a lot of methods for generating word embeddings, like TF, IDF, glove, or bag of words. But these methods, they convert words but don't get the semantic relationship in the context. The recent ones, like bird embeddings, is a pre-trained word embedding model. It gets the full context of the word and the semantic relationships of the word within the sentence. So if you're like me and this isn't enough information to satisfy how these numbers come to be, I learned that training word embeddings from scratch, it's possible, but it's super challenging because there's a large number of training parameters and sparse training data. These models, they have to be trained with a lot of data sets with a lot of vocabulary, and since there's so many parameters, it makes training really slow. So it's pretty difficult to train a word embedding model on an individual level. A very common pre-trained embedding model is called word-to-vec. Since I love math, I decided to look more into how it works. So a word analogy has the form A is to B as X is to Y. In linear algebra, this asserts that A and X can be transformed in the same way you can get B and Y, and vice versa. The vice versa part means that this is an invertible transformation, so we can say that a word analogy F is an invertible transformation that holds a set of ordered pairs S if and only if, for all the X and Y values that are in S, f of x is equal to y and the inverse of f of y is equal to x. So f takes this form, which makes it a linear word analogy. A very famous example to represent linear word analogies is king minus man plus woman is approximately equal to queen. Since this holds exactly true, the vector space actually forms a parallelogram structure because each pair of opposite sides are equal in length. So this linear word analogy holds exactly over a set of ordered pairs S, if and only if the norm squared of vectors x minus y is the same for every word pair, the squared norm of a minus x is equal to the squared norm of b minus y, and finally that the vectors of all the words in S are coplanar. In a transformer architecture of an NLP model, self-attention is performed in parallel multiple times and as a feed-forward neural network, which means that flow is unidirectional and the connections between the nodes do not form a cycle. So we're going to start by declaring x as our sequence, with xi being the ith element in the sequence. Each input vector xi gets linearly transformed into three vectors: query, key, and value vectors. So for example, if you search for a video on YouTube, the search engine maps your query, which is the text in the search bar, against a set of keys associated with the candidate videos in their database. Then you get presented with the best match videos, which are the values. So first you have to compute the query, key, and value vectors for each element in X. Next, we get the attention score. This will be the dot product of a query and a key vector. You have to repeat this process for all pairs of elements. The next step is optional, but it really should be used because it decreases variance in the numbers and it stabilizes training. So once we get the attention score, we scale it down by a factor of the square root of dk, where dk is the dimension of the key vectors. And again, you have to do this process for all pairs of elements. Then we pass the scaled attention score through a softmax function that sums up to 1. The softmax function converts vectors of real numbers into a probability distribution, and this represents the attention weights. So this weighted sum is the self-attention output for x1. We have to repeat this process for x2 and x3 to get the self-attention outputs for all the elements. Then the self-attention of the whole sequence x is the weighted sum of all the value vectors. This is the mathematical output y of using self-attention on sequence x. Q, K, and V are the learned linear transformations of the input sequence, and remember they're parameterized by weight matrices. dk is the dimension of the key vectors, and we use the square root of that to scale the attention scores, and QKT represents the dot product between the query and key vectors. This is usually how people diagram self-attention, which is also known as the scaled dot product attention. In more realistic situations, multi-head attention is used because self-attention is just a single set of learned transformations, whereas multi-head attention uses multiple sets of transformations, or heads. Then the output of all the heads are concatenated and linearly combined to get the final self-attention output. Thanks for watching!